Hello, good morning. Um, who was at the reception last night? All right, all the others are still sleeping. So for those who were, thanks a lot for being here. So this is a session titled Confessions of a Rusty Java Developer. I have stuff to admit. So yeah, apparently I'm not the only one. So there's a thing in this room, a theme with people having to confess stuff. So, so I'm a Java developer. I've been doing stuff with Java for a long time. Played different roles in the Java community, um, in open source work with official JSRs and so forth. But I have not been writing any Java code for over 6 years now. And you'd like Java. I love Java. Java's awesome. I love the language. I love the runtime. I love the JDK. Like, I really enjoyed all those years, but for some reason, I have not been writing any Java for over 6 years. So what happened? So despite Java being an awesome tool, there are just use cases where Java is not an option. So some 6 and somewhat years ago, I started doing development for very different things, not enterprise software or libraries or whatever the heck I was doing before, but I started writing software for this little guy. It's not that small, actually, it's actually pretty big. And music instruments is an interesting problem to address. Um, it's pretty close to real-time requirements, meaning that people that play this instrument, so anybody playing an instrument in this room, right? So probably for the others, there is kind of a relationship going on when you play an instrument, right? There is a feedback that's going on. And so latency is not an option, right? This like effectively a full GC while you're playing a chord is not good. So this part of the instrument actually has no digital handling of the signal for what you hear, but everything is controlled by a computer. So every time you do anything with one of those knobs or whatever, which is what you use to apply some kind of modulation to the sound wave, um, a computer actually is making sure that all that gets routed, right? So sometimes there are cases where you can not use Java, like let's say you'd be targeting like a microcontroller or something like that, right? Java's may not be an option there. So you need to do other stuff. So what people do and how I got started in programming some 30 plus years ago or whatever, you fall back to the good old tools, right? C, C++, any C developers or C++ developers, we can admit it, right? It's fine, it's a confession thing. And I actually love C. I have a relationship with C++. But one downside of those things is actually it's like running with sharp tools is the way that I like to put it, right? And so any humans in the room. So if you're a little bit like me, what happens to you maybe now and then, but actually to me very often, is actually I do mistakes. And those mistakes will result in what we call undefined behavior most of the time actually in C and C++. So things, but certainly bugs, right? Whatever that means. Like the outcome will not be the one you want. And there are many kind of bugs that as Java developers you may not be exposed to, but like use after free, double free, like this many things that when you don't have the beautiful garbage collector to like clean stuff up for you, like that you have to take care of yourself. And if you do mistakes, it's gonna be interesting. So yeah, so that's a bit about me. I'm Alex Snaps, I'm a software developer at Red Hat, and I write Rust most of the time. So anybody has heard about Rust already? Good. Like, keep your hand up. Like, who has Rust running on his laptop right now? Like the compiler or cargo and whatever? Good. Love you people. Good. And who writes Rust professionally here? Like, gets paid for doing it? All right, few people. Okay, this talk might be a little less interesting to you then. So I'm not trying to say that Rust is like the silver bullet, because I think we covered that, not a thing in our industry. But again, right, there are cases where just use the right tool for the job, is what I'm saying. That being said, I think Rust comes with very interesting properties that yeah, that I think you can, hopefully you take something away either from this talk or experimenting with Rust yourself that hopefully makes you a little bit of a better programmer. If that's still an option, because you might all be perfect, but again, I have to confess, I am not. So Rust will not look too different initially when you start looking at it. Like it has your good old C-like syntax, like your curly braces. We all love our curly braces, our semicolon, like all that beauty's there. So it's really nice. It is a strongly typed language. We'll see a bit, some aspects of the type system. It has very strong inference though, so meaning it's not necessarily as verbose as people tend to complain about with Java, for instance, right? It got better, but you less need to repeat all the same things over and over again. In Rust, it can be pushed to an extreme that I like to think maybe sometimes is too much, because like the compiler is not the one that should be reading the code, but humans. So convey whatever it is you need to convey. So statements that are, let's say, two big ones that you'll use most of the time. So variable bindings, simple statements, as you know, we'll see in a bit, pretty much from any language. But other than that, pretty much everything else, not everything, but pretty much everything else in Rust is an expression, which means is evaluated and has such a value. All right, so let's look at this. So that's a bit of Rust code. So for the people who have never seen Rust, that's what it looks like. I made it a little bit weird on purpose. But so you have a function, fn, that's called think, and the arrow specifies the return type, right? So that would be your, yeah. Okay, I should have used something as this U8, because in bytes and Java, but we won't go there. So returns an unsigned 8-bit integer, right? So nothing really too weird. Your curly braces, that defines the body of the function. And then towards the end, there is this println with a weird bang, and then we're printing the result out. So let's dig a little deeper into that, right? So our function, the body. So here we do like a variable binding, prefixed with a let keyword. So we call this thing base, and we assign the value 0 to it. As you see there, there is no type information provided to the compiler, so this actually will be inferred in this case. And so the default is an I32 in this case. The inference is not like var in Java, so the compiler can actually reason things out way further, meaning that if it sees what you do with the value, it can actually say, okay, I need to do something else, and in this case, make it an unsigned 8-bit integer. So this might be a little bit weirder. It's absolutely not useful to express it this way. I just want to highlight those differences. So what we do here, we effectively have an expression that's going to be evaluated. So the curly braces demark like our expression. So we define a scope in which I do the same thing as I did above, right? So I shadow, in this case, the let base, again, specify the type this time. So the way you do this in Rust is with the colon. Then the type information equals 30. Then I do base plus 12, right? And the important bit here is if you look at the last line, it's actually missing the semicolon. So that is what our expression will evaluate to, right? So compiler very good at doing math. 30 plus 12 is obviously 42, which is, as we all know, the answer to everything. So that is the assignment that we do. So this block is an expression that gets evaluated, and the result is assigned to answer to everything, which is what we return from our function. Same logic again, that body is an expression, gets evaluated. We could have written like return answer to everything semicolon, but in this case, I just wrote answer to everything. That is what this function will evaluate to, and as such, that will be the U32 returned by my function. And eventually, we just print this answer so that we know what the answer to everything is. So what's going on there, this question mark that you see at the end is effectively like a function-like macro. For all the C developers in the room, this is not the macros that you know from C. Those are very, very neat macros that let you do like AST introspection and whatnot. They're very powerful, but not part of this talk. Just know that that's the way that they're resolved, right? It's with the bang at the end. So the exclamation mark defines our macro. And so we print the answer by invoking the method think. Nothing really too weird there, right? The way you invoke a function is pretty much exactly like in Java. The 42 gets returned, and we do a string substitution in this case. So the curly braces is where we want to do substitution. All right. So not too weird. So that's what we have. Other than the maybe more expressions, like it's not too weird, I find. There I wasn't too tripped off by Rust initially. So what other differences does the language have, and more specifically compared to Java? So in Rust, you don't have null pointers. One could argue that. So anybody ever had like this thing called a null pointer exception in their code ever, Java developers? Yeah, it happened to you? Okay, happened to me many times. Well, that tries to address this problem, right? So no null pointer, no magic value out of nowhere. And there are no exceptions either. And the two are solved with the same approach. So when you get a null pointer exception, one, you didn't think you'd get an exception to begin with, right? So the control flow, like, oh, this throws an exception. And though we all know that's the case, right? Let's be honest, we all do not necessarily deal with those exceptions, always. And null is effectively, yeah, you get a, well, I shouldn't say pointer because I guess we can't say that. So you get a thing in Java, right? And you expect to have an object at the end of that thing, the pointer. And it was null, right? It's always an option, right? This is just the way this works. So Rust does this differently. It uses enum to address that. And probably the most obvious one would be the option one. So which is the equivalent to the optional in Java. Like anybody using optional nowadays? Yeah, or heard about it? So effectively, this very explicitly represents the fact that when you return something, say you do a method call, right? Think, and we said we return a U8, right? So there's always going to be an answer, effectively, is what mostly we care about saying. We could return an option of something saying that there might be an answer, but there also might be none. So this is how this is expressed. So pub enum option T, so the generic thing probably doesn't scare anybody off anymore in Java, right? We all got used to it like many years ago. It's exactly the same thing here. The big difference, though, is that enum instances are not those singletons like you have them in Java, right? So some T here that could hold some T. Every single option instance that you get back will have its own T, right? It's not like everybody points to the same T, to the same reference. So the way that you use that is pretty straightforward. So let a thing an option some foo, nothing, I just say none. And so I clearly now explicitly represent the absence, the fact that something could be absent, right? So you can't get a null pointer exception anymore. Results are the same kind of approach in the sense that the result is the fact that something can fail somehow. So I invoke something, and maybe I get an OK back of a T, the thing that I expected to get, right? So let's say I'm going to the database, and anybody writing software with databases? Okay, good. So you go to the database, you ask for customer ID 42 because I love that number, and you might get an answer back in the sense there might be no such customer ID in my database, so I get none back. But also things could go wrong, right? So this is where sometimes this gets very verbose because the way you would model this is a result of an option of a customer or some kind of error, right? So it'd be rough like that because yes, going to your databases can go south, like, I don't know, some cleaning personnel comes and unplugs the database server to plug in the vacuum cleaner, no database there, and you don't get an answer, so you'd get an error in that case. So all that becomes very explicit. Any call, what could go wrong if I'm expecting to always have an answer or sometimes nothing. And so the way you deal with that is using pattern matching and destructuring, as it's called in Rust. So the match keyword, think of it like your switch statement or switch expressions, closer to what you get now in Java actually as well. So I'm invoking something in this case, so something might be there, so that's my method call on this thing, something. And now I just go check, right? Was something there or none? In the case of none, we just say nothing to see, move on. And if something was there, I just print whatever the value was that was returned to me. So the interesting part is here is the value in the parentheses, right? We're moving that value from the option that we got into this block expression that's there. And all that is an expression, so because most things will be an expression, so that is how you would get the value out. It's one way of getting that value out of the optional is by matching the results. And now either I give it the default value, nothing here, or the value that got returned, that was held in my optional. So I put this here for reference. Anybody was in Jose's talk yesterday on data-driven development thing? Yeah, so it's all on YouTube eventually, I think. So I would strongly recommend you watch that. So those patterns are now made available to Java developers as well. So you can define those sealed types where I know exactly what the options are. So success, failure, timeout. I actually copy-pasted this from an article by Brian Gutz on InfoQ. That's literally the code as he wrote it. So that I can do the same kind of matching, like a switch expression, if I hopefully use the right wording, over like some kind of an async result, and I can like cases in the case of Java to deal with all the possible outcomes. The cool thing is, again, Rust will know exactly like that you're dealing, like he won't let you leave a branch out, right? If you have an enum of your own type that has 3 possible states, or represent 3 things, like a match statement will need to cover all of the states. All right, but you don't need to do it that way. If you like it, like if match seems kind of weird, so you can just invoke quote-unquote methods on your types as well. So in this case, I'm using this API unwrap or. So in case something might be there, please return me that value. Otherwise, use the one that I'm providing you with, which is pretty much, I think, I don't remember the method's names, but optional in Java comes with kind of the same Fluent API. So you might be wondering how that method appeared. So not very much different than you do it in Java. You can associate functions with an instance type, right? So the way you do this in Rust is using impl block. So I'm writing an impl. It's actually the code from the standard library in Rust. I'm implementing a function, unwrap or, inside this impl block. That does exactly what you saw before. That's what it does. I think I may have simplified it a little bit. I think there are more comments in the code, in the original code, but otherwise, it's pretty straightforward. The one difference that you might notice is that this function takes self as a first argument, which is kind of like your this pointer, I guess, in Java to reference the instance of the option that we're talking about. All right. So far, so good. Nothing too scary, hopefully. But there's actually more, right? So as I said, I started looking into Rust because my C and C++ code was just too broken all the time, and my coworkers would hate me. It's a confession thing, right? So I'm really opening my heart here. So no garbage collector. So resource acquisition initialization is a pattern, I guess, paradigm that comes from pretty present in C++. For those who know, cool. We'll get a little bit into how this works in a bit. Another thing that's pretty different is everything you do will be mutable by default. So if you don't specify that binding points to something that can be mutated, you won't be able to mutate it. So you need to use this keyword that's called mute to say that something is mutable. Otherwise, everything as well is private, and unless it's specified as pub, as you saw before in the code that I showed, right? All right, that's not too bad, I guess, but this is actually where usually things get very ugly. So the absence of the garbage collector tend to make sometimes the code you need to write, like you're sort of yelling at the compiler that's saying, no, I'm not doing this. And you go, well, I'm pretty sure this is fine. And so what's with this? So how do we do this? How do we clean things up, right? So no garbage collector, cool. So this code is absolutely useless, and this is why all the bindings are called useless. They're prefixed with an underscore because we're actually telling the compiler that this is absolutely useless. Otherwise, the compiler will be warning me saying, hey, you're doing this, but this makes no sense. So is this a mistake, or do you actually know what you're doing? And in my case, we all know I have no clue what I'm doing. So, but in this case, so prefixing with this underscore is a way to tell the compiler, yeah, I know I'm not going to use that thing, but just for reasons, trust me. So what I do here is I put my 42 in a box. So box call new, think of it like it's a function defined on the type box. It doesn't take self in this case because think of it as your constructor, right? New there is like, it could be any name. There isn't really a convention there. So box is what I'm doing there is a heap allocation, right? So this will actually put this 42, this I32 on the heap. Now it's allocated on the heap. Somebody has to clean it up, right? The same with the useless 2. This one is 42 as a nice 64, so just waste double the space because it's on heap, so I've got a bunch of space. Let's waste it. So again, inside a scope. So the way this works is that when useless goes out of scope, so in this case at the end of my main function, it will get dropped. Dropped is effectively you're free. Same here, but I define an inner scope, so it's always bound to your scope. That's when you need to take away, right? And the fact that I created it, once it goes out of scope, it gets cleared. So the way that things are cleared is by invoking a magic method, which is called drop. Drop is defined on a trait. A trait is a Java interface, but not really. It's more on, there are differences in the composition and how, in the visibility as well. But consider them like interfaces at this stage. So the way you define an interface is pretty easy. In this case, I say pub trade drop, and it defines a single method that I want those people to implement. And as you can see, it takes a reference to self, so whatever implements that thing. That is mutable. And yes, I did say reference because this time you see this ampersand there, right? The other one was just self. We'll get back to it. So, and that's the way that I can actually implement some kind of logic when the thing gets freed. So think of opening a file, right? When it goes out of scope, you want to make sure it's closed, right? You do your resource management, effectively. So the way that you implement something on the type of yours, so in this case, I create a struct has drop. It has no field, but I implement drop for my as drop type, your struct being your class, say, right? I mean, struct's probably okay. And I just implement the function, right? In this case, I want to debug stuff. I want to know when it goes out of scope, so I just implemented that there, right? Oh, yeah, so the impl part and my method implementation for this. All right, so ampersand reference, what's up with this? So Rust introduces a big concept that's called ownership, and uses move semantic as you would know it from C++ 11 if you're into that. So what's with that? All right, so the idea is that in Rust, there is only one owner of any kind of piece of data. The only ever is one. What does that mean? Let's say I'm creating a string here, jfocus Stockholm, like this string concon from, see, there it's from an str. Strings are this thing that we all believe are kind of straightforward, but it's a very complex thing. So here I'm doing it like a heap allocation for a string, that's jfocus. So now this string on the heap belongs to my binding conference, and I can use it, right? Once conference goes out of scope, we can clean the memory and so forth. What if I put my conference in this infamous optional that we talked about, right? So I move it in there, and that's the key part. I move it in there. So if I try to compile this code, this is not going to work. The compiler is going to give me this kind of a thing, and it's like, what the heck is going on? Well, what happened is I gave the ownership. I moved the ownership of that string, like, well, the conference binding that string to the optional. It's not mine anymore. It's been moved. I cannot use that thing anymore. So the only way to use it now is through the option that I defined there, let option equals. I gave the thing away, not mine anymore, and it can only be one. So what do we do with that? Well, I can borrow stuff, and the way to borrow things is pass them by reference. So that reference, this is stolen out of the Rust book, so it's pretty simple, 2 rules. At any given time, you can either have one mutable reference, so there can only be one thing mutating something at any given time t, or any number of mutable references. So if people want to look at my stuff, like I can lend it to different pieces of code. And any reference must always be valid. So meaning that if the thing that owns it gets garbage collected, right? There cannot be a reference somewhere that still points to that thing, because otherwise it would be a use after free case, right? All right, so this is a quick way of illustrating that. So that's a container type that holds a value t, code to create it, and so forth. But the important one is the pub ref towards the end, right? So what I'm doing is I'm taking a reference to myself, and I'm returning the reference to a thing that I hold, right? Those last 3 lines there. So a reference of type t, of a reference to a t, and the way I return it is by having the ampersand self dot value, right? That returns the reference. So this code, perfectly fine, create the container, get reference 1, reference 2, Like I just checked that the value is the one that I expect. That's all good. That's fine. That works. So what does it mean to be valid at all times? Now, if I move the container inside the scope, as I do here, and return the reference from that scope, I'm allowed to do that. That's an expression. So now let reference should be able to read the value 42, right? Well, actually, no, that's not going to work because I borrowed I'm trying to use borrowed value after the dropping happened of the container, right? Which is what the compiler is telling me here. Like the borrowed value doesn't live long enough because container gets dropped at the end of that line. Same with asmut. This returns a mutable reference to what is the internal. I take two mutable references out of there, and I want to do things with them. Same thing, not going to happen. There can only be one mutable reference alive at any given time t. So the code that you see there will not work. This tends to throw people off a bit during their initial development with Rust. And the way this works, how do you know like how long a reference is valid for is using this thing called lifetimes. And so lifetime are deleted. It's like type inference if you want all the time. So let's have this method that takes two references, 1 and 2, to U32s in this case. Actually, what I'm telling the compiler is this carry notation. Actually, if you write it this way, the compiler is going to go, dude, I'm not dumb. Just delete this. This makes no sense. So actually, there are two lifetimes because there's A and B. Well, sorry, because there's 1 and 2. They're both references. So I can make them explicit. That's done using the generic syntax that you know from Java, but prefixed with the tick. That means I'm talking about a reference now, and now I need to so declare them in the pointy brackets, and then use them afterwards. Again, don't do that. But one thing I can do is this. Now, what I'm saying here is that B has to outlive A. So the lifetime of 2 has to be longer than the one of A. Here, sometimes it gets interesting because bounds on your system. Most people go like this. I went like this. What the heck, blah, blah, blah. And actually, it takes some time to sort it, but the compiler's right there to help you, told you all the shit C++ code that I shipped. And people going, dude, it's segfaults. Yeah, shit happens. And you need to fix it, right? But in C or C++, you actually have lifetime all the time. You need to keep them in your head. Here, the compiler is there to have you back, and in my case, it better be there. So all that leads to interesting aspects. I think that the tools that you get to write Rust actually make it so that you have to write what I call like clearer APIs on the intent that's that you want to achieve. So one example would be what I call, I'm not sure it's a thing, but I call like method dependency. Think of something in Java, and you probably had that, right? Where probably actually the method code would return illegal state exception or something like that, right? Where you need to do something like file, and it's probably not the way this works, so sorry, and no Java for too long. Let's say open the file before you can read of it, right? Or once you closed it, you cannot read from it anymore, right? It's that. Well, all those problems go away because I can move the ownership to the close of the self so that the self goes out of scope, and I cannot read from that thing anymore. The compiler is going to tell me, dude, you're trying to read from something that you said you don't want to use anymore. So writing those APIs and those with that mindset is kind of nice. So here is a quick example I shamelessly stole from a book. So I'm going to create a rocket, right? And that rocket will have two stages, right? Either it's grounded or it's launched, and you can imagine that like they behave differently depending where they are. So the way I do this is by doing this, I called it stage, but stage is nothing special, right? Consider us like uppercase S, we don't care. And then I will store the state that my rocket is in this thing stage, that is phantom data stage. What the heck is that? Well, I'm actually telling the compiler we don't need to care about that thing because there is no state associated with it, as you can see in the struct there. I don't need to actually store at runtimes the state of my rocket now because everything will be specified at the type system. So that's this line. Here's the implementation, though, for when my rocket is grounded. Here are the methods that I want to have there. So yeah, there's this new to create it. I wanted to have the default so that you see it. But the important bit is the launch method in this case I want to highlight, right? You can only launch a rocket when it's grounded, right? That's the important bit. So what we do is, did I screw that up? No, I didn't. The launch method, once it's launched, it actually returns the launch rocket state. So now what I'm doing is I can launch it, I get the launch rocket state back, it just moves the mass and whatever the state that we had. Default doesn't care again, we're telling the compiler we don't care about this. Once the rocket is launched, what I care is that it can go faster, it can go slower. And so I only declare those methods existing when the rocket is launched. And then just for good measure, towards the end here, I have something that exists on whatever the stage, right? Like mass, I can check the mass of the rocket, whether it's up in the air or on the ground. That, quote unquote, doesn't change. So now what I did with this is resolve the problem, right? There's no way for accelerate when I'm not launched, and there's no way to launch when I'm in the air, right? Method dependency, as I call it, decoupled. That's the book I stole this from. I highly recommend you get it once you got started with Rust. All right. So in order, since there can only be one mutating thing, that doesn't seem very useful. There are a bunch of use cases where you want to have like kind of concurrent mutable state or whatever. So how do you do this? Well, actually, the way you do this is what's called like interior mutability. So we're moving, which I think is a good pattern, whatever, right? So in Java, if you have something that needs some kind of coordination and you do this using a lock, a read-write lock, or whatever, move that inside the thing that you care about, right? And so that people using your thing don't need to know how things get coordinated, right? So this might be a little more code now all of a sudden. So what we do here is actually you saw that on a slide before. I've been like on JSR 107, spent too much of my life with writing caches. That seems like an easy enough problem. Why did I spell again, confessions, so much wrong with me. So that's that, right? So I have a cache of things, like I32 to strings, and we create like a cache of like an instance of a cache that we put in an arc. An arc is a atomic reference counted reference. So what this does, it makes sure that now I can share this thing across multiple threads in this case. And when nobody has a reference to that thing anymore, we know it can be cleared, right? Like reference counting is one way of doing garbage collection. It could be done for you in your back. Here it's explicit. So I clone it to another cache. What I do there is I'm actually incrementing that counter, saying, okay, now I got 2 references for this cache. So cyclic barrier in Java, anyone? All right. So a barrier, quickly put, is a way to synchronize multiple threads of executions. When the barrier gets tripped when when all the threads got there, right? So in this case, it's 2. What we want to do is once the 2 thread reach the point, that barrier trips and the threads keep on going. So I create a thread T, moving. In this case, I'm actually telling explicitly that we're going to be moving the things I'll be using inside this closure, your lambda, I guess. So we wait on the barrier so that the main thread actually got a chance to populate the cache. That's what's happening down there. Here, this thread races against the other one, right? So gets there, puts a value in, waits again. So now we know that we synchronize up there, so the value got into the thing, and into the cache, sorry, and now I can retrieve that value from that other thread. This might be a bit much, but the important bit is that you don't see any mute anywhere here, right? And we did mutate, and we did observe that the state mutated. So that's that. That was simple. So Rust is really awesome for other reasons, though. It comes with batteries completely included. So for the people who installed Rust, it's one, I think, pretty easy to get it on your computer. If you use Windows, well, why? So it comes with Rust up that will match all the different versions for you. You can have multiple versions of the toolchain on your system. It will, those comes in streams, so you have the stable one, that is probably the one that you should default to. Then you have nightly and you have other streams. It will take care of your targets, because this is all ahead of time compilation targeted to a specific platform. So let's say you're targeting WebAssembly, for instance, you would download the toolchain to be able to do that through RustUp and then target that. It comes with Cargo. Cargo is kind of your Maven or Gradle. I'm not really sure which one, but I mean, not judging. It will do all the dependency management for you. Comes with this very neat thing that's called Clippy. And unlike the Clippy from Microsoft, this guy is actually useful. You should run it on your project. It will teach you a few things about the language. It comes with entire support for tests. No need to download JUnit or RUnit or whatever. Everything is there, and you can write your test. It even comes for a while now with everything you need to do proper performance testing or benchmarking on your system, called bench, and not shoot yourself in the foot and do it wrong. Benchmarking, anyone here? JMH, anyone? Well, then JMH is what I'm saying. You might be doing it right, but also not. So the standard library comes with a bunch of support. We're not talking like C, I get string, like hash map, vectors, DRC, atomic reference counting, as you saw before. So, and iterators. Iterators is a bit like stream on steroids. We'll see a bit how this looks like. Fun stuff, the useful APIs that I said about, the clearer APIs. So hash map, anyone? Yeah, used that before. So this, and you have kind of the equivalent in Rust, and it comes with a very nice thing that's called the entry API that lets me reason about the absence or the presence of a value in the map. And that makes for very calls like very nice, I find, very elegant code like this, right? Where now I have a hash map where I want to count like the occurrence of a given letter, right? In a sentence. So I hope your JFocus is great, but what I'm doing here is iterating over all the letters in that sentence, right? I get the entry, so whatever the map entry in Java, right? For each letter, and I modify it. So I'm saying, okay, give me the counter for that. Then I difference the counter, add 1 to it. But if it isn't there, or insert the value 1 instead. So no pattern matching or whatever apparent to you, but what's going on is underneath, that's how this is resolved, right? Those two entries will have, so occupied and vacant, will have implementation for those methods and do the right thing so that you can write those fluent thing. So I create a map, iterate over all the characters, get the entry for that thing, so character to a numerical value. I increment it by 1, the and modify, or insert 1 in case it wasn't there. So I find this kind of neat, since we're all about confessions today. I like it. But that sounds like very stupid code that could be written that way, right? Streams and allocating memory and whatnot. That's all very, very bad, right? So I wrote this very optimized implementation of a max method. So give me 2 numbers. I'll put them in an array list, a vector. And I create an iterator over that, think a stream. And then I fold all that, so obviously now I need yet another value. That's very useful. So I'll go for the minimal value for an I32, and I do this closure thing pass the two values in, like look which one is the biggest one. Max is a useful method I have there. Oh, method call on an object, I guess, or whatever. So this must be all very bad, right? Well, and this hopefully now works. We don't care about that. So where am I? Okay, just gonna go like this. And we want to look at this. And yes, indeed, I mean, this is assembly code. You don't need to be able to read it, right? I'm scrolling. You can probably imagine this is not good. I don't see this being fast. Well, actually, the way that this works is not that way, though. If that was like the debug mode, the normal target for you to run your code, but the way that, oh man, I can never see where I am. That is actually what the compiler will do, right? That is, again, you don't need to understand assembly, but I think everybody can agree that those 5 lines are probably way better than the other thing that we looked about. And you don't need to understand assembly to probably guess that there is no heap allocation for an array list or vector, right, and putting all those things in it, right? So that's what Rust calls like zero-cost abstractions, right? The idea is to let you write hopefully elegant code without having to pay the price and performance. And now again, this isn't working, I knew it. All right, so we covered that. So effectively what I did there with the -o is to the compiler that we're targeting release, and please optimize my dumb code for me. Things changed there as well, like Rust comes with overflow checks in debug mode, but all that stuff gets deleted and optimized. Your cert, not like the bytecode generated that could impact, depending on then what compiler will do stuff later down the path when you execute the code. It comes with wonderful support for async, async await, not in standard, okay, in the standard library and in the language and whatever, but the runtimes you get to choose which one you want to use. It comes with what's called no standard, where that lets you do low-level stuff on microcontroller. Like there is no API for opening a file because that's where you are. You deal with it. There is no hash map anymore or whatever. But you can target very low-level stuff by using what you saw before. So option, for instance, is in what's called the core crate, a crate being like a library, and not in the standard one. And that, I think, leads me to the end of all the cool stuff that I wanted to show about Rust. If you have questions, I think we have a few minutes left for them. Since Twitter isn't cool anymore because confession stuff, it's not live streamed and not recorded, so who cares? I don't like Elon. So you can find me on Mastodon. You can go to GitHub/Quadrant. This is where all the code that I write in Rust is open source, right at stuff that we do. And you can scan this QR code that leads me to my blog, where I have a few blog posts about, and more to come on Rust for Java developers. Yeah, I guess that is it. And I probably blew up the time for questions, or maybe I didn't. I don't know. Somebody tell me. But
I think we have time for about one question. So if someone really wants to ask something.
We have a question there. Like, shout it out loud. I repeat it.
I'll come with a microphone.
Okay. Or not.
Hi. So in your rocket ship example, you went with 2 structs for representing the states.
Yeah.
Grounded and the other one. Was there any reason you went with structs? Would it have been possible to do with enums instead?
Yes, you could have had zero-cost abstraction. Like, all that stuff goes away in the end. So whichever version you like best. There could be pros and cons to implement this with one versus the other, depending on what you do with it. In this particular example, we use it as phantom data. We're literally telling the compiler we don't care about this. There's going to be no trace of this stuff in the code in the end. So yes, you could have that, absolutely.
Yeah, and I think we are out of time. So thank you very much, Alex.
Yeah, thank you all for coming. I appreciate the time you spent with me today. And I'll be around if you have more questions. Thank you.